For velocity and momentum, flux profile. So, assume the liquid density is constant and viscosity is also constant. Neglect all end effect because of disturbance. So, we are making the diagram of this question. We have a plate. This is plate. This is inclination on the plate. There, the liquid is flowing over the plate. The distance is L from there to there, and the beta is angle between the inclination angle. So there is a small hole for liquid in the film, and the direction of gravity is downwards. So we will tackle this question by a Navier-Stokes equation. We consider a film is incompressible, Newtonian liquid flowing steadily down a vertical flat plate over under gravity. The film thickness is delta, and we'll assume the flow is fully developed and two-dimensional, meaning variation in z direction are negligible. So, our further assumption is let's outline the assumption. Our first assumption is steady flow, laminar flow, secondly, their liquid is incompressible and Newtonian fluid. And Newtonian fluid. Thirdly, the gravity is the driving force. Fourth assumption is no pressure gradient along the flow. No pressure gradient along the flow, and no pressure gradient along the flow. Then after, the flow is only in x direction, velocity u y. The flow is only in x direction, then our velocity is v of y. No slip boundary condition at the wall. This is common condition in all three cases. No slip boundary condition at the wall. And our last assumption is shear stress is zero at the pre-surface. Shear stress zero is at the pre-surface. So finally, our assumption is completed. So further we are solving the question. So this question, flow of a falling film is solved by a Navier-Stokes equation. Firstly, we will see that the Navier-Stokes equation is three types: the cylindrical, Cartesian, and spherical. In this question, we will use a Cartesian form of Navier-Stokes equation. So the Cartesian form of Navier-Stokes equation in x direction for incompressible flow is the Navier-Stokes equation in the x direction for incompressible flow. So we have used the Cartesian form of Navier-Stokes equation. This is rho dou v by dou t plus mu dou v by dou x plus v dou the Navier-Stokes equation of in the x direction for incompressible flow is rho dou u by dt plus u dou u by dou x plus v dou u by dou x plus vz dou u by dou z is equals to minus dou p by dou x plus mu dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square plus rho g x. This is dou u is all in x direction, but some terms are cancelled from this equation. Our vj is 0 in this condition. That's why this is become a 0. And for further solving this equation, we are get the final Navier-Stokes equation in the x direction is rho dou u by dou t plus u dou u by dou x plus v dou u by dou y is equals to minus dou p by dou x plus mu dou square u by dou y square plus rho g x. This is our final equation this is useful equation for us. So now apply the assumptions. The first assumption is steady flow. By the steady flow, we get the value of du by dt is 0. So this term is become a 0. Second, fully developed, u is equals to u of y du by dy is also 0. So from this equation we get this is also 0. Third one is v equal to 0, no vertical velocity compound. So third one is v equal to 0 because of no vertical velocity is in compound. Fourth one is no pressure gradient. No pressure gradient. By the no pressure gradient, our x in x, our dou p by dou x is also become 0. Finally, the gravity acts in only x direction, so gx is equals to g. Our gravity is only in x direction, so gx is become a g. So by our assumption and this equation, we have final the get simplified Navier-Stokes equation. We get a simpler form of Navier-Stokes equation. That is mu dou square u by dou y square plus rho g is equals to 0. This is simplified of Navier-Stokes equation for flow of a falling film. So now to solve this second order ordinary differential equation, we have to solve this equation by second order ordinary differential equation. So we have to take this rho g on right side. So we have get dou square u by dou y square is equals to minus rho g by mu. Further, we have integrate once of this equation. The integrate one of this equation, we are integrating du, we get dou u by dou y is equals to minus rho g by mu y plus c1. We are integrating this term by y. So we are integrating this term further. This is second integration for our further equation. So if your second integration this equation by dy, so we get a uy is equals to minus rho g by 2 mu y square plus c1 y plus c2. uy is equals to minus rho g by 2 mu y square plus c1y plus c2 is our final equation for Navier-Stokes. So this is very useful equation for us. This is final equation. After this, we are apply on this equation a boundary condition. So what is this equation? uy is equals to minus rho g by 2 mu y square plus c1y plus c2. On this equation, we using boundary condition to find c1 and c2. At y equals to 0, the wall u equals to 0, no slip. The wall u equals to 0, there are no slip condition. Further, our second boundary condition is y equals to delta. The free surface tau equals to 0. Tau equals to 0. So du by dy is also become a 0. Further, apply the condition 1 for this equation. So 0 equals to, this become 0, this also become a 0, only we have C2 and y become a 0, so we have only get C2 equals to 0 by the applying these boundary conditions. So C2 equals to 0 through a boundary condition. So apply the condition 2. If you are apply, this is condition 1. If you are apply the condition 2 for this question, we get the value of du by dt. Du by dy. So we get du by dy is equals to minus rho g by mu dou plus c1 equals to 0. And from this equation we get the value of c1 is equals to rho g by mu delta. So we get C1 from this equation and C2 is 0. So this C1 and C2 is useful for our velocity profile. So what is our velocity profile equation? Our velocity profile equation is uy is equals to minus rho g by 2 mu y square plus rho g by mu rho y by the putting the value of C1 and C2 in that equation. So finally we get the value of uy is equals to rho g by mu del y minus y square by 2. Further, we get the maximum velocity and average velocity by this equation y equals to putting the value of y equals to delta. So maximum velocity occurs at the free surface y equals to delta. So u max is equals to the rho g by mu dou square minus dou square 2 is equals to rho g dou square by 2 mu. This value becomes because of we take the y equals to delta. Further, we solving the question of average velocity. So for the average velocity, we taking the for average velocity our mu dash is equals to 1 by delta integration of 0 to delta u y dy is equals to rho g del square by 3 mu rho g del square by 3 mu. This is our average velocity equation. Further, we solve the volumetric flow rate of that following frame. The volumetric flow rate per unit width. Q is volumetric flow rate per unit width Q is equals to Q is the volumetric flow rate per unit width. Q is equals to 0 to delta integration of 0 to delta uy dy is equals to rho g dou square by 3 mu. This is our volumetric flow rate equation. So, this is all question. So, we are solved this whole question. So, summarize it on one slide. So, our velocity profile is uy is equals to rho g by mu dou y minus y square by 2. This is very important equation for us for further solving. And the maximum velocity is rho g dou square by 2 mu, and average velocity is rho g dou square delta square by 3 mu, and finally our flow rate is rho g delta cube by 3 mu. So, we have solved this question by Navier-Stokes equation. This completes our derivation for the flow of falling film using the Navier-Stokes equation. These equations are widely used in the heat and mass transfer system, especially where thin film dynamics are critical. Thank you.
That if I slightly change the initial condition, it results in a large change in the outcome. And this is where the question gets incredibly difficult. Sure, the Navier-Stokes equations lets us take some state of a fluid and let us predict what will happen in the future, but the chaotic nature of the fluids with turbulence makes it incredibly hard to make long-term predictions. This is why we can't predict the weather for more than 7 days. This is also why we can't predict when we're gonna have turbulence on an airplane. Despite this, the Navier-Stokes equations are incredibly useful. They're used extensively to model aerodynamic objects, for example a plane or a car. Like I mentioned before, the weather forecast also relies on the Navier-Stokes equations. It still remains one of the most important partial differential equations ever. Thanks for watching.